Welcome to those joining on YouTube. So this is our graph theory session. So we're going to the breakout rooms right now.
Greater than or equal to 4.
They are all 4.
Hello.
So therefore, there's a Hamilton cycle, according to Dirac's theorem.
Okay.
Did you find one in this graph?
Do we have to give you the subset?
Chiming in.
So you're going to find, so it says, according to Dirac's theorem, there contains a Hamilton cycle. So you want to find one in this graph. So in this graph, there's 8 vertices.
Right. So 8 divided by 2 will be 4.
4.
And then each degree has at least 4. So wouldn't you just go from A back to A?
Well, the theorem says it's possible. And then the question for you is find one, right? So find a cycle where you can visit each vertex one time and then get back to where you started.
So you'll go from A to D, D to O. Oh, okay. Oh, I see what you're doing. So A to D, D to C, C to B, B to E, E to C, and then E to F, and then back to B.
Yeah.
Yeah, so you could trace it. I mean, you could trace it, or you could write out. It might be easier to write out the letters, right? A.
Well, yeah.
Like
D.
A go to B, B go to, okay.
Yeah, I don't know what it was. You said A.
It was like A to D, D to C, C to B, B to E.
Let's see if I can do it again.
Oh, yeah.
E to C, C to H, H to F, F back to A.
Right, so you can write on it. You could write a list like this, right? So you said A, D,
G.
G.
D
Okay,
doesn't
so-
connect to C.
Yeah, then G goes to B,
To E.
to E, whichever. E or E.
Uh,
A, D, G,
H,
E, B, H, C, then back to A. Okay.
E, F,
D,
A.
F, A. Yeah. So the one that Dan, are you doing with the hearts here?
Yeah.
Okay. Yeah. So that's the one. That's the one I found too. Yeah.
Awesome.
Yeah. I found it. Yeah. So, but this is a test that just says, hey, if you in this case, if you look around and you say, hey, the degree of every vertex is at least half of the vertices that are there. There's definitely a Hamiltonian
But
cycle.
normally you start with the minimum degree, right? You start with the smallest degree first, right? And then you work your way up.
For what?
Because why does it say, in order to describe this, we begin by arranging the degree sequence of a given graph in increasing order.
Usually we arrange it in decreasing order. Usually you do max
Right.
degree first.
And then
So
go
you're doing
down.
it for this one, you do it backwards, yeah.
Mm.
So
But it doesn't
you're-
matter which vertex you start with first, right?
Well, if there's multiple vertices that have the smallest degree, then it doesn't matter which one you start with. But you always have the smallest degree, then the next smallest degree, then the next smallest degree.
All right, so G16.
All right.
So Posat's theorem.
So you're gonna have to read through this too. So the questions are sort of sparse, but you want to make sure that you read the theorem and the conditions, and then try to understand
All right.
before you move to the question.
Sounds good.
Yeah,
right. I'm gonna jump in with another group.
Have fun.
Graph and vertices.
That's a commitment.
Hello.
What up? So the first graph definitely has a lot of Hamiltonian cycles.
Did you find? Yeah. I mean,
Yeah.
you found one.
Yes.
When you say a lot, what do you mean a lot? Like, what does that mean?
Or at least multiple. I mean,
Depending on where you start.
so like since it's a bunch of squares, kind of too, you can do like almost a full square
No, you
and then
can't.
shift over.
No,
They
it's
can.
not, yeah, it's not. That's not gonna work.
Can you
out.
not?
Is it?
Rat. Oh, it's a well, no, because then I can't get back to
Oh,
G.
you were going back to G.
Yeah.
So
Oh, well.
you found a Hamiltonian path.
But there is definitely a circuit because we had one. What was it, John? It was like A to F.
A to F, F to C, C to H, H to E, E to B, B to G,
Yeah.
G to D, D to A.
And then instead of doing it that way, at B, you could have gone from B, D, G, A. So like you can switch those up.
Yeah. Yeah. Yeah, that's the same one I found. I went the other way, but yeah, same one I found earlier. Okay, so then, I mean, it makes sense. Anytime, so the theorem, it's telling you anytime you have at least the minimum degree in the graph is half of the vertices. If that's the smallest degree, then you're definitely going to have a Hamiltonian cycle. But it's not always easy to find them, right? So if you've taken some of the classes with Professor Vorwerk, that's the traveling salesman problem, right? You want to find one of these Hamiltonian cycles. It's not a very easy thing to do, especially in large graphs. So, all right. That made sense though?
Mhm.
That makes sense.
Okay, so as we go along, there's not going to be, like the next question is G16, but try to read through this Pose's theorem and make some sense out of it before you move on to the question, right? So for this part of the book, the questions, there's not so many questions per page, but you're going to have to sort of read and just try to make some sense out of stuff.
Okay.
Okay?
Yeah.
All right, I'm gonna jump in with the next group. Hello?
The two endpoints, A and B. Oh no, that's for a path, right? I don't know.
I think it works for either path or cycle.
Okay.
Let's just try it this way. I'm just gonna call this one A, this one B.
Mhm.
G
That's
A
4 and
equals
3.
4. G B equals 3 and then 4.
Yeah, 3 and 4. So it's 7.
We have 1, 2, 3, 4, 5, 6, 7 vertices. So it fits the
It should be
thing
greater
we were
than or
given.
equal to. Yeah.
Yeah.
So we're good. So it should work, right? Is
Yeah.
that what it's saying?
I think so.
All right. So let's try it then. From those two vertices, make a cycle. Right? So
Nope, that's a path.
So can I chime in here for a second? Are you doing question G18 here?
Yes.
Yeah.
mhm.
So there's two things. So it looks like you satisfied the degree condition, right? So you found two vertices, their degrees were
4 and 3.
yeah, so when you add them up, it's at least 7, which is the number of vertices here. So that's right.
Mhm.
But did you find a Hamiltonian path between those two vertices?
Hamiltonian path between those two vertices.
Yeah, so you're using the path cycle principle, right? So it says,
Yeah.
right, suppose G contains a Hamiltonian path whose endpoints are A and B, right? So first you need two things. You want the endpoints of the Hamiltonian path to be A and B, and you want their degrees to sum up to more than the number of vertices, or at least the number of vertices.
Okay.
So one thing that you want to observe here is if you pick A and B to be adjacent, if they're next to each other, this doesn't really help you out, right? So if the vertices are adjacent, then if you found a Hamiltonian path that went from A to B, it would be pretty easy to extend that to a Hamiltonian cycle,
Yeah.
right? So generally, this is going to help you when your endpoints are not adjacent. So just in this graph E, before we even consider any degree conditions, can you just find a Hamiltonian path?
Between A and B.
No, just between any two vertices.
Oh,
Oh.
do. I just went too far with it.
Are you doing it?
I
Yeah.
forget what I was doing now, but someone else want to try now?
Yeah. Wait, I remember we did one for this.
Yeah.
So I started at this vertex.
It's really bad drawing, but that's a path.
Okay.
That
Yeah.
is definitely a path, right? So now if you think about it, are the degrees of these two vertices, if you add them up, is it more than
Yeah.
Yeah.
at least 7?
Yeah. A
and
is
so-
4. B is
So
3.
the claim is this definitely has a Hamiltonian cycle. Now, Kirsten, with the one that you drew,
Mhm.
can you find a Hamiltonian cycle?
Yeah, if you just connect this.
Right, you would just connect that last edge, right? So those are already adjacent. So if so can I erase other people's stuff on this?
I think.
So let me.
Should I erase it?
Yeah, you can. All right, so I'll illustrate where this might help out. Right, so if we went like this, if that was our Hamiltonian
Oh,
path, okay, so if that was our Hamiltonian path, then the endpoints right here are this and this, right?
Yeah.
Now
Yeah.
the degree of this vertex is 4, right? So the degree of this one is 4, and the degree of this one is 3, which is 7, right? So that's at least the number of vertices. Now there's no edge here for me to connect, right? We're sort of missing this edge that would be right there. So it's not obvious that I could extend this to a Hamiltonian cycle, but in this case, it turns out, yeah, you can, right? And there's going to be a nice way where we can do this switch that we'll see. So it turns out, Kirsten, the one that you did was easy to extend.
mhm.
But this is saying, as long as you can find a Hamiltonian path, which a lot of the times is easier than finding a Hamiltonian cycle, and you're starting and ending points, if they have high enough degrees, then you could always extend it. That's what the path cycle principle is telling you. Okay?
Yeah.
Yeah.
All right.
All right.
So did you all looked at the other ones? You looked at Dirac's and Posa's conditions?
Yeah.
Yeah. And so what did you say? You want to? Can you? I don't know who's controlling this, but
Yeah. Scroll down.
yeah, go to G16. What did you say for which one satisfy?
We said A, C, and F satisfy.
That they satisfy. So can you talk to me? Just like talk me through one of these, like part A.
Okay. In A, we had 1, 2, 3, 4, 5, 6, 7 vertices.
Mhm.
Yep.
Yeah. So we divide that by 2, and that's 3.5. So you can have degrees of 1, 2, or 3. And the highest degree in this is 3. So we concluded that it's satisfied.
Okay, so this one does not satisfy. A does not satisfy.
A does not satisfy.
So why, right? So why does it?
Oh, it has to be, because it has to be greater than 3.
Yeah, strictly, right? So this right
So
here,
Okay.
strictly greater than, not greater than or equal to.
Okay.
Oh, so we did it the opposite way.
Yeah.
Yeah.
So the first one, right? So you want to go up to the middle, right? So here's the midpoint, and you want to look at everything that's less than half. Okay. So everything less than half, so it would be these ones. So this one has to be greater than 1, which is true. This one has to be greater than 2, which is true, and this one would have to be greater than 3, which is no longer true.
Okay.
Right, so this
Okay.
one doesn't satisfy. Mhm. So what about, does B satisfy?
No. No,
No, right?
because the third one's a 3.
Mm-hmm. But which ones do you have to check?
The first 3.
Why do you say the first 3?
That's the halfway point.
Yeah.
But then again, like, so if you look at this right here, that's a strict inequality.
Oh, so the first 2.
Yeah, right. So
yeah.
strictly less than half.
Okay, so
Okay.
yeah, this one would be because this is bigger than 1, this is bigger than 2.
And that's
And
it,
we're just
right?
cutting it off there, yeah.
That's right. So halfway would be 3, and then only strictly less than that, right? So this one would satisfy.
Oh.
All right. So you want to go back and double check these ones?
Yeah.
Yeah.
Okay. So I'm gonna jump in with the next group.
Okay.
Okay.
All right. So
an edge could be added joining vertices. Hey,
Hello.
¿cómo estás?
I'm doing fine. How are you doing?
We're reading this Bondi, whatever that name is, theorem.
Sure. Did you have any questions about the other ones? What did you do? How did you do on the others?
So we looked for this one.
Or even above that, yeah. The post conditions. Did you make sense out of that? Some of the other groups are having
So
trouble.
we went back to G1E, and we were talking about how we first had to find the endpoints.
Huh?
Well, we found the endpoints to be the middle and this.
Yeah.
So we looked at the degrees. This one's 4, this one's 3. So 3 plus 4 is equal to 7, the number of vertices there.
Yeah.
And therefore, yeah, they're
You
considered.
can extend. Yeah, that's perfect for that one. So what about the POSES test there? Did you?
Yeah, that's
the
straightforward.
list?
Yeah, that was straightforward.
Yeah, you wanna just talk through one of those?
Yeah, sure. So for example, for part A, we counted the number of vertices, which happened to be what, 7? 1, 2, 3, 4, 5.
Yeah.
6.
Yeah.
So that means that I must be values between less than 3.5, 1, 2, and 3.
Yeah.
So if we look at the first degree, it's 2. So 2 is greater than 1. 3 is greater than 2. However, 3 is not greater than 3. So Post's theorem does not satisfy this
Correct.
condition here. However, B, it does, because if you look at B, there's 6 vertices. So 6 divided by 2 is 3. So I must be values 1 and 2. And if we look at the first degree, 2 is greater than 1, 3 is greater than 2, therefore it satisfies the condition.
Perfect. Yep, you got it. Yeah, and then the rest of them are the same.
Right. So B, A, and same. Daniel, which one was it? It was
A and D.
That didn't satisfy it, but the rest did. Do you agree? Disagree or agree? Or?
So you said A doesn't. So we did A and B at the other group. D, you said D definitely doesn't because of the 4th position, right?
Right.
Let's
But
see.
the rest do satisfy Post's degree.
This one, yeah, C does.
Yeah, B, C, E, and F, they all satisfy besides A and D.
1, 2, 3, 4.
I kind of enjoy doing those. It's pretty sick. You just divide 2. It's got to be less than that number, and then look at the degree sequence. Pretty straightforward.
I agree. I agree with you, Edwin. That's good. No, you when you talked through it, that was.
Now, the only reason why I know this is because the first homework had to deal with all that, so I had to
You had to think about it. Good.
I had to review that.
Good.
So that's the only reason why I know, kind of.
Yeah. So question 2 says, it talks about the relationship between Dirac's theorem that you just talked about, and then Post's. Yeah. So you have to put those 2 together.
So now I'm gonna So Yeah, so right now we're in G, what?
You're
Oh, no, so we're reading this theorem. So we're trying to like interpret.
sense out of this.
It's a little weird. Like
Yeah.
thingy cycle and like, I don't know. But yeah, so G be a graph with n vertices where n is greater than or equal to 3. I suppose that. So G prime is a super graph, right? Because I was watching a video on those videos that you be posting, those Sarahada, or whatever. And she was talking about G prime being a super graph,
Yeah.
and then G being like a subgraph of G prime.
Yeah. So it means you take a graph and then you can start adding edges in.
Right.
So same, you don't add in any vertices, you're just adding in edges.
I did. Okay. So like an example of that would be like a complete graph in a cycle, right?
Correct. A cycle is a subgraph of a complete graph. Correct.
Okay. All right, cool.
So what you're going to do is just kind of like the past cycle principle. You're going to be looking and checking if the sum of the degrees is high enough.
Right.
And what they're saying is you can then start adding in edges, right? So you'll start adding edges in. And if eventually you can add in edges and find a Hamiltonian cycle, then you don't actually need those added edges in the original graph. That's what they're saying. So if you think about this, hey, if I added a bunch of edges into a graph, it would be easier for me to find a Hamiltonian cycle.
I kind of need to see that visually. Like, I need you to like, I don't know, make a graph and just like kind of.
Okay, so let's, like scroll down a little bit.
Like a base case or so. Oh, there's more graphs down here?
Yeah, so there's like this, right? So one of the questions down here, like, so the claim is like, let me annotate here for you. So in this graph over here, is there a Hamiltonian cycle?
Boom, 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 boom. Yeah, there is.
Yeah, right. It's just this right here.
Just go around. You just go around the house. Yeah. Okay.
Right. So that one's pretty easy to find, right?
Mm-hmm.
Okay. So if I come over here in this graph, it's not as easy to find.
Which graph?
This original one.
Oh, okay, right.
But the claim is, if you could find one in this graph, you should also be able to find one in this graph. Okay? And what you're allowed to do is you can start adding edges into this graph G. Okay, so what we can do is, let's get this stamp going here. All right, so our second graph, we'd have 1, 2, 3, 4, 5, 6, right? So we're gonna we'll add some edges in here. Okay, so these are our originals.
Right.
I'm not adding any edges.
So
I'm just copying this.
Copy and pasting. Okay, I see.
Did I get them all?
Yeah.
Boom, 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 boom. Yep, you got them all.
Okay. So what we're saying is, hey, you can go ahead and you're allowed to add an edge. You can add an edge somewhere, but the only time that you can add an edge is if the degree sums are high enough. So if I look over here, this is 2, and this is 2. 2 plus 2 is 4.
Wait, I can't. Which one are you pointing at?
So let's talk about this edge right here.
Okay.
So we can't. I'm not allowed to add in that edge right there, because the degree of this, right? So the degree here is this degree is. Oops. This degree is 2, and this degree is 2.
Right.
So 2 plus 2 is not at least 6. So I'm not allowed to add that edge in. But now let's think about it a little bit differently. Is there a place that I could add, oh my gosh. Is there a place that I could add an edge?
To make it so it equals 6?
Or more, 6 or more.
1, 2, 3. You can add an edge to this corner one here, right?
Yeah, you could add an edge. Yeah. So that would be 3 and 4, which would be 3 and 3, which is 6. Yeah. So you can add that edge in, And now, if you can find a Hamiltonian cycle in that new graph with the purple edge added, the theorem says then you can also find one just using the blue edges. Okay? But this is not, you don't get to stop here. You can keep going. Okay, so now you can do it again. So you can add another purple edge in if you want to, as long as the degrees of the two vertices sum to at least 6.
So, whoa. Okay, so what if I was to add a vertex edge on to this here?
Yep, you could definitely, then you could add that in, right? Because that was a 1, 2, 3, 4, and a 2 makes 6
So it has to be greater than or equal to.
to the number of vertices. Yep.
Okay, I see.
So now what you did after step 2 is you said, okay, now if I can find a Hamiltonian cycle amongst all those edges, red, purple, and blue,
Mhm.
then you can find one using just blue.
So just using G.
Just using G, yeah. Now, but you get to keep going. You can even keep going more than this, right? So if you want to keep going, can you add in more edges?
Yeah, can't you? Yeah, oh, okay.
You can add that one too, right? Because that's a 4 and a 2. Now, you could even add more. Can you add more edges in?
Yeah, now you could add the other two, right? These. Would you add these two?
Then you can add that one, right? Yeah.
And then that's it. Then you would have this graph.
Then you have that, right? And we already found a Hamiltonian cycle. So the claim is, hey, if you can find a Hamiltonian cycle in G prime over here on the right-hand side,
right?
You should be able to find one in G using just the blue edges.
Okay, so the first thing we do is we look to see if we can find one in G prime. If we can, then there must be one in G.
Provided that you added edges in this way.
Okay.
Yeah. So it's the underlying principle here is if there's more edges, it's probably going to be easier to find that Hamiltonian cycle. And so the theorem gives you a condition that says, yeah, you're allowed to add in edges as long as you add them in this nice way where you only connect vertices that have high enough degrees.
Well, I actually found it's from here. Boom, down, up. Wait a second. Oh, never mind.
Yeah, you're good. Now go down, right?
Down, yeah, okay. Up and then to the right. Okay, cool.
Right. So the claim was you found one in G prime. It was easy to find one in G prime. So then you can definitely find one over there. So it just gives you another strategy to find these things. So you're all familiar with the statement of the traveling salesman problem. You've heard that before. So it's
yeah,
really
isn't that a problem
right?
that's never been solved or something like that?
I mean, we have solvers for it. It's just it's hard to do in general. Yeah, there's no fast way, right? So there's I'm using an ambiguous definition for fast here, but yeah, I mean, it's really hard to do it quickly. So the millennial problems, right? So it's a NP complete problem. So if you're familiar with the P versus NP millennium problems stuff, it falls into that NP class of problems. And so in your mind, what you can think of, it's hard, right? It's hard. It's a hard thing to do, right? So there's a lot of technical definitions for NP, but think about, hey, it's a hard thing to do.
Okay, so now for G21, they gave us G prime, correct?
That's G. So now
That's
you're
add
allowed
edges.
to add in edges,
Okay.
but only if their degrees are
Greater than or equal to n.
That's right. Yeah,
Okay.
at each step.
All right,
Okay.
All right, thank you, Professor.
All right, you're welcome. Keep going. I'm going to jump in with the next group.
All right.
All right, cool.
All right.
All right,
See if
so
we can
let's
do this.
see.
Hello.
What up?
Okay.
How are things?
You're going.
We're on 21.
Okay. Did you find the sequence in this graph above?
Yeah.
Yeah, so you go connect these two because I don't like that.
Yeah.
You connect these two because they're both 3 and they're the only ones that add up to 6. So now this one has 4 and you can connect it to that one because 4 plus 2 is
Yep.
also 6.
Yep.
Same thing down here.
Yep.
And then 3 plus 3 is 6. And
Yep. And now you've created this graph over on the right.
Yeah.
Where's the Hamiltonian cycle in this one on the right? Pretty easy to find.
Just hexagon.
Yeah.
They just go around
Oh,
outside,
there we go.
right? Yeah.
Or,
Okay, so that made sense to you,
Mm-hmm.
this condition. Okay, so the big picture here is if you have more edges, it's easier to find a Hamiltonian cycle. Do you believe that? Right, more edges.
Yeah.
yeah.
Generally, right? So certainly if it's the same graph and there's more edges, more opportunity for me to use things, it'd be easier to find it. And so this gives you a condition that says, yeah, you're allowed to add edges provided they have this degree condition satisfied along the way. But now you're thinking about G21.
Yeah.
Mhm.
Okay. So you're I mean, the other groups are right where you're at.
Yeah.
So any questions for me so far? Anything you wanted me to clarify or?
I just had a question, but I feel like it's written there, but I'm just gonna ask anyway. So in the first graph G, like this condition only works if there's already a cycle in the graph, right? And then you're just finding another one.
No, so what we would think is we're not sure, right? So perhaps you're not sure if there's one in G,
Mhm.
and you want to do something to make your life a little bit easier, right? So the question would be, is there a Hamiltonian cycle over here?
Mhm.
At first glance, it's not obvious where it is,
Mhm.
right? But it is obvious over here.
Okay, so this just helps you find out that there is one in the original.
Correct. Yeah. So you've heard of the traveling salesman problem?
Yeah.
Some of your other classes, yeah.
Mhm.
So this is the traveling salesman problem, right? You want to visit all the cities once without repeating.
Mhm.
And so finding that route is a really hard thing to do. And so what these are doing, right? These theorems are giving you a way to make your life a little bit easier, right? So instead of finding a route over here, we don't know if there is one or not. We want to go ahead and make our lives easier, add some edges in, and still be guaranteed that by adding in those edges, we're not ruining anything from the original graph.
Okay. That makes
So
sense.
if there isn't a cycle in there, how many, like, could you just keep drawing paths? Or is there, like, eventually you're going to run out of extra edges to put?
Correct. Yeah, then you should run out, right? So if there's no Hamiltonian cycle in the original graph, then you should run out of edges.
Okay.
Right. So there'll eventually be a place that it's not valid, right? So the degree sums are too small
Mhm.
everywhere amongst all pairs. And then there's no more edges that you could add in.
All right.
How would they be too small if you're adding edges?
Because you need to find a pair of non-adjacent vertices that have high enough degree sum, right? So if we let me think of an example here. All right, so let's take a path on 5 vertices. Okay. Now the claim is, so obviously there's not a Hamiltonian cycle in this graph, right? There's no cycle there. So what we would want to do is we would ask, hey, can I add an edge? Can I add an edge to this graph? Well, what I would need is the 2 vertices, if I add up their degrees, I would need it to be more than, or I would need it to be at least 5.
Yeah.
Okay. So can you find a pair of vertices whose degree is at least 5?
No.
No, right? So there's no opportunity, there's nothing, there's no pair of vertices that satisfy your degree condition, so there's no valid edges for you to add in this one, right? So it's not just saying that like you could take any graph and extend it just by adding edges randomly. You need to have those particular vertices whose degrees are high enough, right? So you could have really graphs that what we would say are sparse, meaning there's not a whole lot of edges in them compared to the complete graph, and you just would never have those two vertices of high enough degree, right? So you could imagine a graph with 1 million vertices, and every vertex has degree, less than 5, right? So then you're never going to find a pair of vertices whose degrees add up to more than 1 million. Okay, so with it's sometimes that's hard to see because a lot of the textbook examples have graphs that are like 5, 6, 7, 8 vertices. But remember, these graphs, right? So if you think about like the networks that we're dealing with that are enormous, rarely are you going to have vertices of really high degree, right? So like if you think about people on Facebook that are friends, like there's nobody out there that has half of the people on Facebook as their friend, right? Like that's just
that'd be absurd.
Yeah. So so some context there. Does that kind of answer your question with the there could be a place where there's nothing to add, there's no valid place to add.
Yeah, it makes sense.
Makes sense.
Yeah. John, good?
Yep.
All right, so what are we thinking? We're thinking about 21 here?
Yeah.
Yes.
So for this one, you would add these two at first because they equal 7. And then you could add these ones.
And then there's a Hamiltonian cycle.
Yep.
They want you to show how only one step is needed now.
So for B, that's where we're
Yep.
Okay, so we consider the degree sequence. So
the degrees are 3, 4, 4, 3, 4, 4, 3. So it's 1, 2, 3 3s, and then 4 4s.
3 3s and 4 4s.
I write that.
Isn't there a 5 in there, John?
Yeah, there's a 5. That's a 5 right there.
Which one am I missing? Oh, okay. I'm sorry, I miscounted on that one.
3
So
3s,
yeah.
3 4s, and 1 5.
Yep.
Oh, there's this one.
Okay, so
All right.
So
I'm gonna let you keep thinking about this. Somebody else asked. Yes, sir.
I'm kind of confused on this one.
Whoa.
So such that G contains 2 edges of AI and BV, and which are these 2 edges here. For example, these extra edges can be AV2, so AV2.
They're a little complicated.
Okay, so what my confusion about this is stemming from, I don't understand where the restrictions on I are originating,
So look at the. So you don't understand the. Let me highlight something. This bound. this bound right here in blue?
Yeah.
Mm-hmm.
Okay.
So I'm
So saying
yeah.
the idea of this proof, so we want, so you tell me, start from the beginning and tell me the story of what sort of happened here, where the confusion is.
Sorry, would you mind just scrolling up a little bit so I can see?
Yeah. Oh wait, I gotta take out.
Cool. All right. So
I'll
I
clear out
understand that it's like the path. They bend the path so that it's, you know, that bent path thing.
Yep. So this down here. So they bended this to make it look like this,
Yep.
and then from there, they're saying that you could add edges so that hold on. So they're saying if there's an edge here, then obviously there'd be a Hamilton cycle, which is pretty clear. So, but we're looking at the case where A and B are non-adjacent.
Mm-hmm. Well, if they are adjacent, you're done, right?
Yeah.
Right, because you could just add an edge there and then be a cycle. But if they're not adjacent to each other, then this is where this comes in, where they drew this edge and this edge. But they're saying that there must exist some I where it has to be between these two conditions, such that G contains the two edges, this and this, so these two edges here, shown in the diagram below. For example, these extra edges can be, so they're saying that these edges could also be from here to here. Oh, sure.
Yeah, so where's the Hamiltonian cycle in this graph? So basically what they want to do is you have a path and you want to guarantee that there are two more edges in this graph that appear next to each other.
Mm-hmm.
Okay, so yeah, okay, so whoever just highlighted that's your new cycle, right?
Mm-hmm.
So what do you want here, right? You want to make sure that you can have this I and this I plus 1, both of these things down here not being, you don't want this to be A and you don't want this to be B.
Right.
Okay?
Mm-hmm.
So if I is 1, that's great. This thing is not A. Okay? And you don't want I plus 1 to be B. Right? So you don't want I to be this vertex, right? So you don't want to be taking this edge as this.
Yeah.
Okay. So if we do that, right? So the 1 says, so this 1 right here is telling us, hey, you don't you don't want, oh my gosh, this writing. Okay. I'm gonna try here. So this 1 is saying you don't want your first vertex to be, you don't want this to be A. And you don't want this to be B.
All right. I see that. Yep.
Right.
It's complicated.
And so that's where you get these inequalities here.
Mm-hmm.
Okay.
All right.
And so, but the claim is, the whole proof is you're going to prove that you can find this edge and this edge right here somewhere. And then what you're doing is you're taking the path that was around like this, and then you're just making this little figure 8 thing. Okay, so if you can find these two edges, if you can guarantee that they have to be in there somewhere, then you'll be able to generally extend your Hamiltonian cycle.
Okay.
Mm-hmm. All right.
Okay, does that help out? So so that's kind of the answer to this G22 right here.
All right, that makes sense. Okay.
They made that needlessly complicated when they explained it.
Yep.
Thank you.
A little bit.
Well, yeah, I mean, they're trying to be rigorous, right? So they're trying to be, yeah. Sometimes when you're really precise, you sacrifice clarity for precision.
Yeah.
Mm.
I can see that.
Yep.
Okay, so I think G23 does help out though with this idea.
Let me see.
Okay.
Cool. Cool.
We got 1:45. So a little bit of time.
Okay, so let me erase this here.
I'll clear out my stuff. Yeah.
Okay.
So let's clear this. So there's an obvious path, right? A, V1, V2, V3, all the way out to B. So what we want to do is we want to find two vertices so that we could make this swap, right? So B is going to be adjacent to the lower index, and A is going to be adjacent to the higher index, right? So you want something like 1, 2, 2, 3, 3, 4, 4, 5.
Yeah.
B to be adjacent to the lower, and A to be adjacent to the higher.
So are we looking for one that exists or one
Yeah.
that could exist?
Yeah,
one
so
that
you're not
exists?
adding edges in this case.
Okay. Cool.
So whoever starred those 2, 3, so you want A as your starting point to be adjacent to the lower, and then B as your ending point to be adjacent to the higher.
I would think B has to be adjacent to the higher index number.
Lower, sorry. B is adjacent to the lower index number.
Okay.
A is adjacent to the higher index number.
So you could do like that.
You could.
But they have to be consecutive.
So by
So
consecutive, they have to
B
be like,
goes to the lower index,
yeah.
and then A, right? So then A goes to the higher index.
Yeah. Okay.
So these orange lines would be right.
That 1, 2 would work. Yep. So 1, 2 is a good example of that.
So that means that would B be after that would be V3. Oh, so you just only look at 2 edges, or are you continuing on from there?
Yeah. So the path goes like this, right? So the path is along the outside. 4, 5 also works. Whoever checked those off. But now the question is, okay, so can we extend this path? We found this path. Can we extend it to a cycle? And so since you had 4, 5 checked, right? So we would go down this way. We would go up. We go down, and then we go back around like this.
Okay. And so it's saying that whenever you can find the path and then you can find the two vertices satisfying that condition, you would automatically have a Hamilton cycle.
Yeah, so the general would be take A, go down here, take this sort of bridge, finish your Hamiltonian path that you found, then jump back down like this, and then come back around. So we did, this is the general case, and we did kind of the same thing over here.
Cool.
All right, so now, so we're saying if, right, so if you could find such a situation always, then that's going to guarantee we have a Hamiltonian cycle. And so down here, we want to try and guarantee that we have such a set of vertices.
Okay.
Do we steady the ship here, or we?
Wait, so so we didn't use V6 because of the condition up here, correct?
Correct. If you want it to be, you don't want your second vertex to be B.
Okay.
Yeah, so we don't want to choose 6 because then the next one would be B. We didn't want that to happen.
So A would be connected to V5 and B would be connected to V4?
Yeah. So Dan, did you highlight 1 and 2 would also work here?
Yeah.
So where A would be for 2 and B for, okay. All right.
Yeah. A would be to 2, B would be to 1. Yeah.
And 3 and 4 would work as well, right? So
3 and 4 will not work.
and the reason why is because B is not connected.
So you want B to be, because A is not connected to V4.
4, that's why. Okay. I see. All right, it makes sense. Yeah.
Cool.
All right. So that's why we chose these two and V1 and V2.
Yeah, either one. You don't need there to be multiples.
Right.
It just needs to be one.
Just one of those pairs.
Yeah.
Cool.
Okay, that makes sense. Which Hamilton cycle results?
So we got about 10 minutes left. I'm gonna do a quick check-in with the other groups, and then I'll bring everybody back together.
All right, sounds
Very
good.
cool.
All right.
Thank you.
You are welcome.
So for the graph in problem G23, define two sets of numbers S and T in the following way. List all the vertices that are adjacent to A except for V.
Oh, there he
Then
is.
how do I? Oh,
Hello.
Hello.
hi.
How are things?
We're
We
pretty sure
finished
we're
up
done.
G21.
You're done. You did G21. Did you keep
Yeah.
going?
Mm-mm.
You can just keep going if you want.
Are we bringing it into a bigger group again before you're in class, or?
Yep, we will. So I'm making my final laps around here to see if we had any individual questions.
We're just kind of honestly confused as to like what the Bondi, I don't know how to pronounce that.
Bottle.
Theorem was actually like what the point is of it. I don't know.
Okay.
It was kind of confusing.
Can you scroll up a little bit on the screen? All right, so yeah, just to the top of that page, Sharon.
Oh, right here?
Yeah, so I can see G and G.
Okay.
So let's erase this A, B, C, D. Where I put that on there.
I
Okay.
think that's me, maybe.
I can clear it.
Okay. So here's the sort of big picture idea. If I look at this graph over here, G prime, pretty easy to find a Hamiltonian cycle in that one.
Yeah.
Right?
Yeah.
Now you just kind of go around the edges, go right around the outside. Pretty easy to find one. If I come back over here to G, I mean, you might be able to find one if you looked for it, but it's not obvious. Okay, so it's not obvious where it is in this one. There is one, but it's not obvious. So what this Bondi-Schwartz condition says is, hey, you have the ability to make your life easier by adding in edges. Okay, so if you can't find a Hamiltonian cycle, what you can do is make your life easier by adding in edges. So specifically, I'm able to add in this edge right here. And by having that edge, presumably it's easier for me to find a Hamiltonian cycle because now I have more choices that I can go through, okay? And if I can find a Hamiltonian cycle in my new graph with this new added edge, the theorem says you can also find one in the original graph somewhere without using that edge.
Okay.
But it's actually stronger than that because I can then say, I can do this again, right? So I'm gonna add in this new edge. So let me go back here. So if I check again, the degree of this vertex is 1, 2, 3, 4 now, even with this green edge. And the degree of this vertex is 2. So 4 plus 2 is 6. I have 6 vertices. So I can add in this edge. The theorem says, if I can find a Hamiltonian cycle in this graph with the green edges, I can find one without the green edges. But I get to keep doing this. I can do this iteratively as long as I keep having vertices with high enough degrees. So now this one has 4, and this one has 2, so I can connect this. And now this one has 3, and this one has 3, so I can connect this. Okay. And now I have this graph over here. Right, so in this graph, in this new graph with the green edges, I can find a Hamiltonian cycle pretty easily. And the claim is, okay, well, since I can find one in this with the green edges, I can also find one without the green edges. It doesn't tell you where, but it tells you that it does exist somewhere in that graph. Okay, so if you're just checking, hey, is a graph Hamiltonian? Does a Hamiltonian cycle exist? This is a way to give you an existence proof without actually constructing it. And so let's see if we can actually find one here. So it turns out that we can, I think, like this, right?
Yeah.
Okay.
Yeah. Right. And so, but you didn't use any of those new edges that we added in, right? So you found one without one. And so that's what this condition tells you. You know, you don't have to use those additional edges. And you still guaranteed to have a Hamiltonian cycle.
Okay.
So Chris, does that make a little bit more?
Yeah, that
More
makes
sense?
more sense.
Okay. So you've heard of the traveling salesman problem in some of your other classes, right? And
Yeah.
probably
Yeah.
will work. Okay, so this is the same idea, right? You want to visit all the cities exactly once, return home, and then finding that, right? Actually finding a Hamiltonian cycle or finding this route for you to travel and visit every city once is not an easy thing to do, right? So it would be great if we knew whether we should be looking or not in any case, right? So it might be impossible. Sometimes computationally, it's really, really hard. And so these kind of theorems tell you when you should definitely not even try looking or when you should try looking. Okay, so yeah, we've got 3 minutes. So I'm gonna bring everybody back together so we can wrap up here.
Okay.
Okay. All right, I'll see you back in the main. All right. So you're going to be muted as you come back in here. Hello, hello, hello.
What up?
Hello. Okay. So recap. As I was going through it, I think a lot of us, we made actually really great progress today. So the goal was G21, and I think everybody made it to at least there. A lot of us were thinking about the proofs, right? So the proofs of these conditions in the other one. So today, at the very least, you saw the 3 conditions, right? So you saw Dirac's theorem, which says if the minimum degree is at least half the vertices, then you're going to have a Hamiltonian cycle. Pose's condition allowed us to check just the smallest degree vertices, right? So we had this condition that said, hey, if you look at the vertices of the smallest degree and they're big enough, you're good. You're going to have a Hamiltonian cycle. And then the Bonish-Vital condition said, hey, what we can do is we can actually make our lives a little bit easier by adding in edges. So provided we only add edges again, where the 2 vertices have high enough degree, that's going to make our life a little bit easier. We have a new graph with more edges. That would be easier to find a Hamiltonian cycle in. And so the end of this, right? So the end of this chapter goes through some of these proofs, right? So what I would like to do on Thursday is see of the 3 proofs. So I know some of us were already working through the proof of the past cycle principle, but if we could get through the 3 proofs there, Bonish-Vital and Dirac and past cycle, that would be awesome for Thursday. So we'll see how far we get. If you want to, it might be helpful to read through, because some of this now it's really going to get into some hard thinking, because we're actually going to try to prove these conditions. Where today we just saw some examples and made sense of them. So it's probably going to be helpful if you can just sort of read. It's only 2.5 pages, but try to think through some of these and where you get stuck, and then we'll bring those back to everybody on Thursday, right? So those places where you're not quite sure about what's happening. But with that said, I think for the homework, at this point, you should be pretty familiar with all these things, and I think the homework should be pretty manageable for everybody. So does anybody, well, we have 0 minutes left, but I'll kick it over to you. If there's any burning questions or anything that you wanted me to address before we go for the day?
I think I'll probably pretty much just email you if I have any other questions on the homework and stuff like that.
Yeah, you can always email me, and then I'll get back to you. But All right, so we'll call it there, and then on Thursday we'll try to finish up these proofs. So again, I had a great time seeing you all. I look forward to our time each week, so I'm glad you all come in and join us. So I'll see you all on Thursday.
Bye.
Bye, everybody.
Bye.